In this video, we are going to be continuing our discussion about the topic of multiplicity in proton NMR. So, understand that I discussed previously the idea of the signal being represented as a singlet, as a doublet, or as a triplet. Understand that there are other patterns that exist out there, and they are actually illustrated in table 15.3 in the textbook. If you have the third edition of the textbook, table 15.3 can be found at page 672. In the table, you can see the number of neighbors. How does that relate to multiplicity? And then what are going to be the relative intensity of the individual peaks? Now, understand that analyzing the splitting pattern of a signal in the proton NMR is going to help you determine the number of equivalent protons that we have on adjacent carbons. The reason why we have here the graphical representation of what the alpha and beta spin states are is because remember that in this technique specifically, the idea overall is that we're going to have an external applied magnetic field, and what that is going to do to our charged particle is the creation of a magnetic field. And then the resonance that is going to happen in the technique is when we have the alpha spin state convert to the beta spin state, and as we have the movement from alpha to beta back to alpha, that's what creates the resonance. Okay, so whenever we're talking about all of these concepts, we're also always thinking about the applied external magnetic field and then what happens to the different spin states and the magnetic fields that are created by those moving charged particles. That being said, understand that the trend that we see on table 15.3 also allows us to predict splitting patterns. Now, previously we were just looking at how many neighbors do we have and then how many peaks are we going to predict. Understand that in organic chemistry, when it comes to this concept, we have what is called the N+1 rule. Okay, when there are n number of neighboring protons that are chemically equivalent, there will be an N+1 splitting pattern at the particular nuclide that we're looking at. Okay, so there are in general 3 key rules to always remember when it comes to splitting. Okay, rule number 1: equivalent protons cannot split one another. What does this mean? That if you have homotopic or enantiotopic protons in a particular molecule, because they are chemically equivalent, they are not going to split each other. Now, for protons to split each other, understand that these need to be within 2 or 3 bonds of distance. What does this mean? That, for example, the splitting can be observed if we have geminal protons, and then in the geminal case, then we are talking about diastereotopic protons, or as we seen in the previous example, vicinal protons, meaning that the proton is in the neighboring carbon atom. Okay, now understand that splitting is generally not observed if the protons are going to be too far apart. So as you can see here, proton B, because it is 2 carbons away from proton A, it will not create a splitting pattern on A. if there was a proton on that middle carbon, then we can assume that that HB will be affecting it. And because it's in the middle between HA and HB, understand that there's a possibility that they are going to create a splitting pattern. Now, the last rule states that this N+1 rule only applies to protons that are all equivalent. What does this mean? That if we look the molecule in the bottom and we are going to focus in, or we're going to focus on the hydrogen that is in the middle that I just highlighted in red, if we look at its neighbors, okay, which I'm just going to highlight in green. When we look at the neighboring protons, the one that it is on the left, this is part of an sp3 system, okay? It's a tetrahedral, or is part of a tetrahedral carbon. The one that is on the right is part of a carbon that is actually sp2, okay? So this is a vinyl group. So in this case, this N+1 rule will not apply to the hydrogen that it is in red because the protons that are neighbors are not equivalent to each other. This proton that we see in red is going to have a more complex splitting pattern because when we look at the protons that are their neighbors, they are not equivalent to one another, okay? Now, let's understand that the degree to which neighboring protons will couple to its neighbor, it's called the coupling constant or the J value. J value in essence is going to be the distance between the peaks of a splitting pattern. It is going to measure in units of hertz, okay? So protons that are going to be splitting each other will have the same coupling constant. So as you can see here, we have an example in which we have a haloalkane that HA contains 2 protons, okay? And again, the reason why it shows up as a quartet is because that splitting, that graphic is actually given by the neighbors that we have, the 3 protons on HB. HB signal is going to be determined by the number of protons that we have in HA. So this is why it is a triplet. And again, the J value, because establishes that it is the distance between the peaks in the splitting pattern that is measured, understand that since these protons are going to be splitting each other, they're going to have the same J value or coupling constant, as you can see, determined by the space that we see here illustrated in the patterns that we see for each one of these signals. Now, understand that the higher field strength instruments is going to give a better resolution, okay? When it comes to looking at certain molecules in which sometimes the proton patterns are going to be really close in the spectrum for proton NMR. So I just wanted to illustrate an example here in which we are comparing a specific set of protons for the molecule that you see below. This is an ester, and we are actually focusing on the protons, okay, that are labeled with the letter B. If we actually visualize that signal at a 300 megahertz spectrometer, understand that that which is the peaks that we see specifically on the right side, so this is the 300 megahertz. We see now that specifically the protons that are on labeled with the letter B, because we are going to see a quartet, we see it much better in the figure B, or on the figure on the right, as compared to if we actually do the reading on a spectrometer that is going to have a lower frequency, like in the case that we have a 60 megahertz. So when we see the same signal, as you can see, now we don't have the clear view of the quartet that is going to be present for that signal. This is just illustrating that depending on the specific spectrometer, you can have a better resolution. Now, understand that sometimes recognizable splitting patterns will stand out in a spectrum, okay? So let's actually look, for example, at what we have in the following molecule. As you can see in the molecule, we are specifically looking at the CH2 and the CH3 part of the compound, okay? So an isolated ethyl group is going to give a triplet and a quartet. Remember that the triplet is going to be the CH3 because its neighbor has 2 hydrogens, okay? The quartet is going to be the CH2 because its neighbor has 3 hydrogens. Now, understand that the triplet and the quartet must have the same coupling constant if they are splitting each other. So for example, if we look at the signal that we have in the bottom of the slide, that does not represent an ethyl group because the way that these signals appear, the J values or the coupling constants are not going to be equal to each other. So this is going to represent a different group. Now, let's understand that when it comes to these signals, we also need to require to look at the integration, okay? So understand that a peak with integration equal to 9 is going to be suggesting the presence of a tert-butyl group. That is just in general. And then if you actually see that it is a singlet, it makes sense because they don't have neighboring protons. They are all attached to a central carbon atom. Now, if we look at the multiplicity, for example, for an isopropyl group, that specifically is going to give a doublet and a septet. Because remember, the septet is going to be the single hydrogen that has those 6 protons as neighbor plus 1. That's where the septet comes from. And then the hydrogens on both CH3s are going to be equivalent to one another, and since they have the hydrogen as their neighbor, that's why it shows up as a doublet. Again, the integration is what's telling us the number of hydrogens that we have in the signal. This is just different key factors that we need to take into consideration whenever we are putting the information together. Now, understand that complex splitting can result when a proton has 2 different kinds of neighboring protons, okay? But for example, here when we're looking at this molecule, is very different from the example that we talked about before, because in this example, the 2 carbon atoms are both sp3s. So it's very different from the example that I explained before, which the neighbors were different, okay? So let's just handle this example. So in the molecule that we have shown here, okay, if we think about HB splitting pattern, we need to take into consideration that the neighbor to the left has 3 protons. The neighbor on the right, it has 2 protons, okay? So technically, when we think about it, the split there is going to be a quartet by HA into a triplet by HC. Now, understand that also the J value, the coupling constant, is going to play a role of how this is observed. If the J value is much greater for the coupling constant between AB is much greater than the coupling constant between B and C, then the signal will appear as a quartet of triplets. Okay? What does that mean? A quartet of triplets is that we have 4 triplet signals. If the coupling constant for B and C is much greater than the coupling constant between A and B, then the signal will appear as a triplet of quartets. That means that we're going to have 3 quartets. Now, understand that if the coupling constant is similar for B and C and A and B, then there are going to be several lines that may overlap, okay, all together, and that is just going to be called a multiplet, because at this point we just have them all build into each other. So there's just going to be a whole bunch of lines coming together, and then the multiplet is illustrated here in the bottom of the slide. Now, understand that splitting is actually not observed for some protons. Let's now specifically consider the example of ethanol, okay? So ethanol is going to have 3 different types of protons, okay? And I'm going to highlight them. Well, let me just first start by writing the protons on the carbon atoms. So as you can see, we have the protons together in the CH3. We have the protons from the CH2. And lastly, we have the proton that is in the hydroxyl group. Now, understand that the protons that are bonded to carbon will split each other, okay? But the hydroxyl proton will not split, okay? So if we have to number the molecule and we have to determine what these signals correspond to. If we look at the second signal, this is a quartet. Okay, so the quartet most likely is going to come from the CH2. Okay, because remember that the neighbor has 3 protons. The triplet that we have upfield is going to come most likely from the CH3, because remember its neighbor is a CH2, and this singlet that we have in between 2 to 2.5 is going to refer to the proton in the hydroxyl group. So understand that this hydroxyl proton, okay, and there's other exchangeable protons, can undergo rapid exchange with a trace amount of acid. And as you can see here, this is just the acid-base mechanism that illustrates the exchange of that proton. In the presence of acid, the acid is going to donate a proton to the alcohol, but then the water that is generated can pull that proton back. So the protonated alcohol gets deprotonated. Understand that in such exchange, then the shielding, deshielding effect from the neighboring protons is going to be given a singlet, okay, that is often broadening. And this concludes the discussion on multiplicity.